And let me make sure that you will see my face and my whiteboard in the recording. So today we will take it from where we left it yesterday, obviously. We were talking about the string. I'm just gonna continue as if we have been never interrupted, but feel free to stop me if I'm going too fast, if there's anything that requires a further clarification. Yeah. And so let me briefly summarize what we have done so far concerning the string problem. A good part, I think, of last lecture was devoted to carrying out some physics consideration to convince ourselves that realistic enough mathematical description of the string of an elastic string that's under tension is the following equation, where on the left hand side you have a second derivative with respect to distance along the string, and at the right hand side you have a second derivative with respect to time, and they are connected by a proportionality factor that turns out to coincide with the ratio of the tension of the string to the density of the string. I'm calling it C squared. I'm using a power of 2 here to remind myself that this is a positive and real number. It's not any number. This is determined by the physical properties of the string. It's a ratio of the tension that has been administered to the string divided by the density of the string. Also, at this point, the problem we are treating is still very abstract because we are talking about an infinite string, a string of infinite length, okay, which doesn't really exist obviously in the real world. Then we applied our knowledge of partial and ordinary differential equations to see how actually to find a solution for these problems. What we did was to apply separation of variables which in practice meant writing u, which is a function a priori unknown of space and time, as the product of two functions. The first, depending on distance on space alone, the other, tau, depending on time alone. We have shown that this strategy actually works and results in finding, it results in breaking the second order partial differential equation PDE into two second order ODEs. You've realized by now that ODEs are usually somewhat easier to solve than PDE, and in fact, we were able to find several possible solutions to this ODE. We have also found that a general form for the general forms for the solutions of these two PDEs are for psi, we have psi of x equal some, for now, arbitrary constant a times the cosine of the square root of minus lambda divided by c multiplied by x plus b, the sine of the same thing. Okay, and for tau, we have some other constant. Please be patient with me and let me call it A prime because I'm already running out of letters. A prime cosine, it's basically the same thing, right? As you remember. Square root of minus lambda times t plus b prime sine, I'm going to write the whole thing now, minus square root of minus lambda times the time t. So you remember from our little review of ODEs that a second order ODE is solved, and I should add a second order homogeneous ODE because remember the ODE that we got has no is a homogeneous equation. It doesn't have a function in it, a term that doesn't contain psi of its derivative. So what we got was the second derivative of psi equal to lambda over c squared times psi itself. So it's a second order ODE. And you remember from our review of ODEs that solving something like that means finding a linear combination of two linearly independent solutions that well, of that same equation, and that's exactly what we have in here. Okay, I didn't give you a mathematical proof for that, but sine and cosine are indeed linearly independent from one another, and so this is enough. Okay. Good. So that solves our abstract infinite string problem. If the string is infinite and if we don't specify some initial state for the string, we cannot say anything else, anything more about these problems. Okay, maybe we want, well, yeah. I don't think it's worth to discuss this infinite string with no initial conditions problem anymore. But this can be and is also a useful result to apply the moment we impose some linear conditions of the string. We now ask that the string be finite, or in other words, that 2 points of this string, for example, be fixed. So we we focus now on the problem of the so-called guitar or violin or piano string, whatever your favorite instrument is. So we now specify that 2 points on this string are fixed, and I'm going to call, and I'm going to introduce also a reference frame where the first point, the first endpoint of the string is called 0, it's the origin, and the second point is at a distance capital L from the first. And now what I'm saying, in other words, is that I'm only interested in solutions here such that u at x equals 0 is 0 for any time t, and also u, the displacement at x equals L, the displacement at x equals L is 0 at all times t. Okay, so the string is still a string. The physics that we've the individual element of the string obeys the same physics whether the string is finite or infinite. So most of what we've done yesterday still holds, but now we want to eliminate from our spectrum of possible solutions those that do not satisfy this condition. Those equations, those functions cannot exist in our world. They cannot be observed on our real world string. So let's see what happens. Let's see how in practice we achieve that. Well, remember that these equations contain two arbitrary constants. Actually, three in a sense, because lambda is undefined yet. Okay, so let's see if we can constrain their values by imposing on this expression these conditions. Okay, so the first condition reads also psi of 0 times tau of t equals 0 for any value of t. But that means that basically, if we want this to work, I mean, we have two possibilities. Either tau is 0 at all times, which means that the string is not moving, is not doing anything, which is an absolutely valid solution, but that's it. It's not very interesting. So sure, the string can stay still, of course. But what if it's not staying still? What could it do then? Well, then we have to consider the case where tau is not necessarily 0 at all time. The string is doing something. Okay, so we are left with the condition that psi at the point 0 at the first endpoint is identically 0. So let's look at what these can tell us. Well, if I plug 0 in here, the cosine of 0 is 1. Okay, so for this, and the sine of 0 is 0. So we are left with a cosine of 0 equals 0, which necessarily implies that a is 0. So one of the arbitrary constants is gone. And we are left with the condition that psi of so and we cannot say anything yet about b because the sine of 0 is 0. So, but we have another conditions, right? And now we are left with psi of x equals to a0. So we lost it. So b multiplied by the sine of square root of minus lambda over c multiplied by x. And I'm interested now in what happens when x equals L. So please allow me to just replace X with L in this expression. And now I know that this has to be equal to 0. So that this is actually kind of interesting, because this doesn't give me any information about B, but it does give me information about lambda, because look, of course, again, I could say, okay, B equals 0. Yes, B equals 0 satisfies this equation. So if B equals 0, I have a solution. But again, that's called a trivial solution, okay? If both A and B are 0, again, everything goes to 0. Xi is identically 0. The string is not moving, okay? It's not a big discovery. The string, again, is physically allowed to stay still if nothing happens to it. But there's a second possibility now, and it is that the sign here, okay, that we forget about B, and this whole thing is verified if the sign of this guy is 0. And the sign of this guy can be 0 if lambda has some particular values. So when is it that the sign of a number is 0? When the number is a multiple of pi. So if I write that minus lambda square root divided by c times L equals k pi, where k is an integer number, can be 1, can be 2, can be 3, etc., up to n infinitely large, then this condition is satisfied. Now, L, it's the length of the string, so it's defined by the physics, by the physical condition, by the setup of our experiments. Once we have both the guitar, we cannot change L unless we buy another guitar. C also, we define it when we buy the string. We decide how heavy, how thick we want it to be, and by tuning the guitar, we administer some tension T to it. Okay, rho and T define C. But lambda is an arbitrary constant that emerged automatically when we decided to solve this equation by separation of variables. So lambda at this point is free to take any value, okay? So in this equation, if I solve for lambda, I get that the square root, I'm going to make some room up here. We don't really need this stuff anymore. Well, we do, but you remember it by now. So I'm going to solve the equation to the bottom right of the whiteboard for lambda, and I get that the square root of minus lambda coincides with k p c over capital L, which means also, if you prefer, that lambda is equal to minus k p c L squared. So notice that for this equation to be verified, therefore, for this boundary condition to be verified, these are called, I don't know if I use this term, but these are called the boundary conditions of the differential equation. So for this first boundary condition or second boundary condition to be verified, lambda has to be real, negative, and equal to all that, where pi is pi, 3.14, blah, blah, blah. C is depends on tension and thickness of the string. L is the length of the string. So everything is real. K is an integer. Okay, and it's got to be negative as well. Okay, so we have a spectrum of values of lambda. I'm going to call them lambda k to distinguish them from one another, which means that we have a lambda 1 that's equal to minus pc over L squared. Lambda 2 equals to minus 2 pi c over L squared, lambda 3, and blah, 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 okay? And so on and so forth. Okay, so let's see what this does to our solution. Well, this was our initial expression for psi is right here. Okay, this is what comes out of the theory of differential equations. But we discovered that A is 0, so this first term is gone, and we are left with psi of x equal b times the sine of square root of minus lambda, which is 2 pi c over L, I'm sorry, pi k pi c over L, square root of lambda k, divided, remember, divided by c, so this cancels out, times x. So we removed a lot of the arbitrarity in the solution by fixing, by specifying that the endpoints of the strings are fixed. And you should notice now that this, because tau and psi are related to one another, right? The same constant lambda, this has to be the same number here, otherwise everything we've done falls apart. So if you are happy to replace the lambda in the spatial function with these values that we found, you have to accept that we need to do the same thing for the time-dependent factor of the solution. So now we know that our tau has, like the cosine and sines in our tau also have to contain this very lambda. If I put a minus sign in front of it and take the square root, I'm gonna get k pi c. This time I don't have c in the argument here, so c doesn't cancel out, divided by L times t plus b prime, the sine of the same thing. Okay, let me make some room. Okay, so what does that tell us about displacement? Okay, well, easy, relatively easy. Now, displacement on the string, we know that the way we've addressed the problem, it's got to be the product of psi and tau. Okay, so let's just write it down. The general solution, the general form for solution must be the product of these two guys, A prime B times the cosine of K P C P over L times the sine of K pi X over L plus B prime B, the sine of this first guy here, times the sine of K pi X over L. So I guess I shouldn't say that this is the general solution. This is what I've written on the blackboard, is on the whiteboard, is rather I've written a spectrum of possible particular solution. For each value of K, I have a solution that looks like this. It's kind of cumbersome now to carry this A prime B, B prime B. Let's just call these two products, I'm just gonna call them, I don't know, alpha and beta. Or something like that. Okay, just to simplify things a little bit. Do you have, like, have you been able to follow me so far? Do you have any question, comments, doubts? Good. Excuse me. Good. So what can we say? What can we do on top of this to further understand, to further explore the physics of our problem? Well, what this says, essentially, what we've learned so far is that on an elastic string of finite length with fixed endpoints, whatever solution, whatever displacement has to be described by this formula. The string can stay still if both alpha and beta are 0. This is verified and the string is not moving, and that's a perfectly valid solution for the problem. Not very interesting, but valid. Or the string can vibrate, it can move. If it moves, its displacement has to be described by this apparently complicated, but we look into it in a minute, combination of sines and cosines. Before we start making drawings of how this thing looks like, let's add a further consideration. What determines whether the string moves or stays still? I have to excite it somehow, right? So one way to prescribe an excitation is to deform the string with respect to its equilibrium position. If the string is still, it's not moving, it's in a perfectly straight shape, the vertical component of the tension is 0. So remember our derivation yesterday, if that thing is 0, the acceleration you derive twice with the differentiated twice with respect to time will also be 0. If the acceleration is 0, u will continue to be 0 and the string will not move. But if I deform it and then let it go, the moment I deform it, the vertical component of the tension is not 0 anymore. And the moment I let it go, it will create an acceleration, and then the system will start to oscillate. If you've done a harmonic oscillator in school or in your undergrad, it's not very different. It's basically the same concept. So let's see how it works in our setup with the string. I impose now some initial conditions. So after the boundary conditions that gave me, that simplified my solution in this way that you've seen, I'm going to prescribe some initial condition. And I'll for the time being, I'd rather be general and say that the initial condition is just some sort of initial, well, it can be in the most general case. I could also like give some initial velocity to the string. You know, if you hit it, if you hit it from a position where it's not moving, actually what you do is you prescribe an initial velocity, and maybe the initial displacement could be 0. So I will apply initial condition on both the initial displacement u, and that would be some sort of function f of x that describes the initial setup, the initial form of the string. If I just pull it like this, it will be a triangle, for example. And then a second condition on the velocity of the formation. Again, notice at time, conditions at time equals 0. And velocity can be described by a function that I might call lowercase g. So I'm going to make a little bit of room now. Give me a second. Right. So now I mentioned, okay, that this is not a general solution. This is a spectrum of particular solutions, and the general solution of the PDE should be a linear combination of all possible particular solutions. So we can write it in the most, so this I should call UK, which is the product of psi k and tau k, because each of these corresponds to one value of k. But in the most general case, we're going to have that u of xt is the linear combination, is the sum with k that goes from 1 to infinity of alpha k cosine k pi c t over L sine the k pi x over L plus beta k sine of the same thing. And then again, the sine x over L. Great. All right, so I don't even need this guy anymore. So let's first think of the initial condition let's first think about the first initial condition. At time equals 0, the stuff that's inside the sum here can be simplified quite a bit, because if t is 0, this sign here goes to 0, and the cosine here is just 1. So we are left with the sum of alpha k sine k pi x over L. And my first condition is that this has to be equal to some prescribed function f of x. In practice, when I solve a specific real practical problem, I will have to decide what f of x is like. So like I said, if all I'm doing is taking a point of the string and pulling it, it will be a triangle. But for now, again, let me stay general, and let's just call, like we find a formula that's valid for any function f of x. Now let's think about the second condition, that it's a bit more tricky, because we have to differentiate this guy with respect to time. So let's differentiate u with respect to time. What I get is alpha k, the derivative of the cosine is minus the sine, and I have, of course, to multiply this by everything that multiplies t in the argument. So k pi c over L times the sine of k pi c t over L plus, but wait, well, yeah, plus, now the derivative of the sine is the cosine, so beta k, same, I'm going to play the same game here, so cosine of the same thing. And of course, this is all multiplied by the sine of k pi x over L. But now, again, at time t equals 0, the sine of 0 is 0. So this first term here goes away. And we are left at time equals 0, del u over dt at t equals 0 coincides with the sum of just beta k, k by c over L. The cosine of 0 is 0, sine of k by x over L, and that's it. And this has to coincide with some function, arbitrary for now, that I call lowercase g of x. Okay, so now now here's a trick that one plays to find to actually turn the initial conditions in some mathematical formulas for alpha k and beta k. And the trick is to use a known properties, known if you've done a bit of calculus. If you haven't done it, I guess you can look it up or believe me. But it's not so hard to prove, if you have some time to spend on that the integral between 0 and some fixed number, for us it's useful to choose L, of the sine of I pi L x over L times the sine of j pi of x over L is equal to L halves delta ij. What does delta ij means? It's what mathematicians call the Kronecker delta. The Kronecker symbol, but it doesn't matter. Basically, it's 0 if I is not the same of j as j, and 1 if I is the same of j. So what I'm saying is that calculus teaches us that the integral of the product of two signs where the argument is a constant times pi times x, well, a constant times x multiplied by an integer number, multiplied by the same thing with another integer number, is going to be 0. Okay, this function, the mathematical expression, if you like, it can be that these two functions are orthogonal to one another, unless the integer number here in the argument, unless I and j are the same. If I and j are the same, if these two signs are the same, then they are not orthogonal anymore. And this integral gives me L halves. If instead of a sign here, I put a cosine, then it's always 0. The sine, and remember, the sine and the cosine are linearly independent. Their product is 0 in the product, the scalar product. Well, anyway, calculus again accept this result of calculus that the integral of a sine and a cosine with such arguments, even if the argument is the same, would be 0. So what does this mean for us in practice? Well, it means that, look at this equation here. Let's manipulate it a little bit using what we just found out. Let's multiply, nothing forbids us from multiplying both sides with the same thing. So I'm going to multiply both sides. This is not good. Okay. I'm going to multiply both sides with the sine of j, okay, pi x of L, where j again is an integer number. Okay. And I'm going to do the same thing on the right-hand side. Okay, and then also nothing forbids me from integrating both sides along x from 0 to L. Okay, but now look, the integral at the left-hand side, if you believe me that you are allowed to pull the sum outside of the integration, okay, these are two linear operators, so we can interchange them with one another, it's okay. They're basically two sums, so it doesn't matter in which order you sum. Then this integral is exactly this integral, right? I'm just, sorry, this integral, I have just k instead of I, but this is L halves delta k j instead of delta j. Okay? So that's basically and also another result, I'm sorry, of calculus is that excuse me, I'm like quickly looking at my notes because I don't want to say any, I don't want to forget any little constant. So that the integral of just the sign from 0 to L is 1, I think there's a pi somewhere. Anyway, let me make some room because this is becoming a bit cumbersome. So here you get the sum from k1 to infinity L halves delta kj alpha k. And here, and let's simplify this. L halves I can pull out of the sum, and everything within this sum will be 0 except for the case where k equals j. So I'm left with just alpha j. And yeah, actually, I cannot simplify this integral. Sorry, I had a moment of doubt. I cannot simplify this integral unless until I make a choice for f. So for now, we just leave it like this. And that's basically it for now. Okay, so you can divide both sides by L halves. And basically, this gives you a possible strategy to compute numerically, and if f is particularly simple, even analytically, the values of alpha j. Analytically, by analytically, I mean that you might even be able to find some mathematical formula, depending on how f is like. And now I'm going to skip it because it's at this point, it's time consuming and not particularly instructive for you, but you can basically play this exact game with the constraint that we have on the that we obtain from the initial velocity. Remember, you have an equation for the velocity that looks sort of like this one, with a slightly more complicated coefficient here. And you can do exactly the same thing, and you end up with an equation that looks like this with a slightly more complicated coefficients on the right-hand side, but the method would be exactly the same. Okay, so does that make sense? Questions, anything? Good, excuse me. So I would like now, I give you a couple of minutes. I'm not sure that my speed is right. So I give you a couple of minutes to think about this before I delete everything and move on. So what I hope to have convinced you of so far is that the motion of a string is described by this seemingly very complex expression, where L is the length of the string, C is the ratio. I always get this one wrong. So C is the square root of tension to density of the string. Tension, remember, is a force per unit area that has a tendency to elongate the string, and rho is the density of the string. And I've also shown you that these coefficients here, alpha k, and k is any integer number. Well, actually, it's already in the formula because I'm already summing already. And I also hope to have shown you that alpha k and beta k are not just some abstract things, but are something that is numerically determined as soon as you know what the initial state of the string is. So alpha k and beta k can be determined for every value of k are known through our initial. Okay, so mathematically, in terms of mathematical manipulation, I think I have done more or less as much as I could hope to do. But now I would like us to think deeply about what this equation means. So let's see, how can I show it to you? Well, let's think of a strange case, for example, where all the values of k are, all the values of alpha k and beta k are 0, except for the first one. That's something, it might be hard on a guitar string to actually make it happen in practice, but physically, it's something that can perfectly happen. We proved that it's perfectly possible. So let's assume that we have a way to exciting our string in such a way that all the alpha k's are 0 except for the first one. Basically, if you remember by previous equations, I'm saying this incidentally, all you have to do is have an initial condition, an initial shape of the string that coincides with the sign of 1 times pi times x times l, the first, what we call the first eigenfunction, spatial eigenfunction of the string, because the coefficients is obtained by multiplying eigenfunctions with one another. That will basically realize exactly the situation. But we'll I'll get back to this later. For now, let's just assume that you can put yourself physically in a situation where alpha 1, and maybe there's no initial velocity, so we make it even simpler. Alpha 1 is 1, and everything, all the other coefficients are 0. Okay, this is something that's allowed to happen on our string. So in this particular case, u of xt is just the sign, excuse me, the cosine of kpc over L times t times the sine of k p x over L. Okay, so let's see how that looks if we were to take with a very powerful and quick camera, if we were to take a lot of picture of the string as it vibrates. So at the time t equals 0, that's easy because the first factor here is 1, cosine of 0 is 1. So all we have to do is to write, and sorry, here k is equal to 1, right? So is to write the sine of pi x over L from 0 to L, to L. So the sine of 0 is 0. The sine of pi is the sine of pi is 0, and right here, if I substitute L halves in this formula here, I get the sine of pi halves, which is 1, right? So it's going to look like this at time equals 0. As time passes, the cosine here, which is 1 at time equals 0, will take a slightly smaller value. So at time equals 0 point something, I'm just writing 0.01 like that. I don't know exactly. Everything is not in scale here, right? But anyway, a small time after, a small fraction of a second after the initial time, this thing is going to be moving a little bit. The cosine becomes smaller, so the amplitude of the displacement is smaller, and the string is moving back towards its initial position. And at a subsequent time, the cosine will be even smaller. And if you wait long enough, eventually the sign of the cosine will change, and we will jump on the other side. The sine of pi x over L, it's always the sine of pi x over L. So as time passes, we're just multiplying this guy by a function. So now some jargon and this is, it's musical acoustics if you wish, but we use exactly the same terms in seismology, as you will see. This sign here, this function that describes the shape of the string at a given moment in time, that it will change in amplitude, but the general shape will be the same. This is called the eigenfunction, spatial eigenfunction, or normal mode, or mode of the string. And like, so like you have it right here. For each k, there's a mode, and this first mode, it's called the mode associated with the lowest possible value of k, which is 1 in our formulation. It's called the fundamental mode. Everything that you get for larger values of k, those are called overtones. Okay, so the fundamental mode is of a string of length L is sine pi x over L, and to this mode we associate an oscillation in time that's described by either the cosine or the sine, depending on the initial condition, of k of pi c t over L. So what I'm doing here, I'm defining a quantity that I call frequency, which is the argument of the time-dependent factor here, except for t, and that describes how fast this oscillation is. If you think about it for a minute, you can convince yourself that if a frequency is very small, it means that you will need to change if you need to wait quite a bit of time, you will need a large change in t for the string to change its position. Okay? If the frequency is higher, in the same amount of time, you will have a larger change in the form of the string. You will have a larger change in the cosine and or the sine of, cosine of omega k t. Okay? So basically, how much, in a given amount of time, if I decide how much time I'm going to wait, if omega is large, the argument of this guy changes more, and so the string is moving faster in time. Okay. I really would like to make sure that these concepts are crystal clear. So as an exercise, I will also repeat quickly the same idea for the first overtone, okay? So the first overtone is what we get if, well, it's what you get if you replace k with 1 in here, or in other words, if all these coefficients are 0, except, say, for alpha 1. So let's think, so that the spatial eigenfunction would be the sine of pi x over L, which gets multiplied by the cosine of, I'm sorry, the sine of 2. The first overtone, we have the sine of 2 pi x over L. We replace k with 2. I'm sorry, because we called 1 the fundamental mode. So to get the first overtone, now we have to replace k with number 2. Excuse me. Sorry about that. And the cosine, accordingly, we have to multiply the fundamental frequency by 2. So now we have the cosine of 2 pi c over L times time. And now, if I, like, the sine of 0 is, like, let's first draw, let us first draw the spatial eigenfunction, the normal mode. The sine of 0 is obviously 0. Now here we have, if I replace x with L in here, I get the sine of 2 pi, which is 0. At L halves now, when x equals L halves, I also get 0, because if I substitute L halves in here, I get pi. The sine of pi is 0. At L quarters, L divided by 4, I get the sine of pi halves, which is 1. And here I get minus 1, the sine of 3 halves pi. Okay, so this is how the first overtone looks like in space. And then in time, the string will oscillate like this, and eventually, oscillate back and forth like that. With a frequency now that, as you can see from here, omega 1, the fundamental frequency was just pi c over L, and omega 2 was is 2 pi c over L, and so on and so forth. So you, at this point, I think you can start imagining what happens when we go to higher overtones, but I let you think about that by yourselves. And what I want to do now, unless you have any questions, I want to think about the physical meaning of this in terms of how a musical instrument works. And what we discovered in practice is that there's only discrete, infinite but discrete set of frequencies that are allowed to happen on these strings. Once we've chosen L, once we've chosen C, okay, so we've bought our guitar, we bought a string, we mounted the string on the guitar and we tuned it. So we chose how much tension we want to have on the string. Then the frequencies that can occur on that string are fully determined. Okay, and they are, what are they? Well, omega 1 is pi c over L. Omega 2 is twice that. Omega 3 is 3 times that, and so on and so forth. So remember what I told you yesterday. Our ear is a strange thing. Our ear, together with our brain, we function mysteriously. We function in such a way that every time we hear together two frequencies, two sounds at frequencies that are an integer multiple of the other, we derive from that some sort of basic sense of pleasantness. We perceive this sensation as something good. This course is not about why that is the case. I don't think we really know why that is the case. It's just a fact of nature that we can verify experimentally every day. So that's exactly what a string with fixed endpoints does. By construction, and this is what we've proved in this last hour, a string can only generate frequencies that are multiple of one another. A sound that is a combination of frequencies that are multiple of one another, we call a note. Okay, so when I say A or B or C as a musical note, if you care about these things, you should know that I don't mean one frequency, but I mean a frequency and its overtones, okay? I don't have a guitar here, unfortunately, but if I hit randomly a guitar, I don't have to decide where I hit it, how I hit it. It doesn't matter. It will always generate a set of frequencies that are multiples of one another, depending on how I hit it. And this is something that I should go back to when I talk about the initial conditions. I went pretty quickly today about the initial conditions. So we'll do that again on Friday, or maybe we have time today. So depending on how I hit, I can excite one of these modes more than the other. Okay, so it just happens that if I hit the guitar string near the fixed end, near the bridge, as musicians call it, of the guitar, I will hear more of a acute, high-pitched sound. If I hit straight in the middle, where the fundamental mode reaches its maximum value, I will produce the gravest, the deepest possible sound, okay? Because I'm stimulating the fundamental mode more than all the other modes. Questions, doubts, comments? So I would like to, like I said, I would like to have a minute, or maybe a bit more than a minute, to touch again on the initial conditions and how we use them. And again, we can make some quite fundamental physical considerations based on that. So let me go back to what I wrote a few minutes ago. can probably delete that. All right. I've shown you that if if we prescribe the initial state of the string, that's one way to describe the way we hit it, the way we play our guitar. So if we say that the initial, well, let's use mathematical symbol. So the initial shape, the initial position of the string is described by a function f of x. So if I just pull it like that at a given point, this could be f of x. And we prescribe also the initial velocity. And then as a first example, we can decide that the initial velocity is 0. So that's something that you can easily do by yourself. You take your guitar, pull it at a given point, and let it go. Don't pull too hard or you'll break it. And plus, you know that all this theory works for small deformation. So you don't need to like, what I mean is that this is not in scale. Okay, we're always talking about very small deformation. Otherwise, the theory doesn't work. So, so let the initial velocity be 0. Keep it simple. Then I showed you that the coefficients up there are determined numerically by these two equations, which we obtain using the properties of the integrals of sine and cosine over a fixed length. This is a bit different because there's a derivative involved, remember? So we didn't do it, but if you do it as an exercise, you should find the formula that I'm about to write. And again, the sine of this now, if f of x is if sorry, I mix them around. Sorry about that. Okay, the first one was no, that's okay. Yeah, I'm not sure what I wrote before, but the first one should be F and the second one should be G. So if G, yeah, I think I had exchanged them. Sorry about that. I was reading my notes. So make sure that you get this right, okay, in your notes. Okay, these two equations. Double check that your notes look like my whiteboard. Good. So the second one, if G is 0, everything is 0. Okay, so beta K is 0, and that's easy. So let's forget about this. We are left with this sum. Now let's think about this a bit longer. If the initial shape is coincides. Okay, imagine that you have a lot of fingers. Imagine that you can put your guitar in a shape that resembles that of one of the modes, say the sine of J pi x over L in here. Well, this is either 1 or 0. Remember the properties of this integral that I mentioned a minute ago. So if the modes, these two modes are different, it's going to be 0. If you want to really excite a mode as much as you can, you start from that mode. You excite specifically that mode. You put the string in a position that resembles that mode. So, for example, in this case, if you have an overtone that looks like this, right? Maybe the first overtone looks like this. So exciting the string like that is a fairly efficient way of exciting this overtone. So your ear will hear the frequency, will hear very well that frequency that's associated with the first overtone, which is 2 pi c over L. So if you're talking about an A and the fundamental mode of your string is 440 Hertz, a Hertz is just 1 oscillation per second, so one up and down per second, then you're gonna hear 880 Hertz, most than other modes. But if you excite, like look, this is kind of interesting actually. Now, if you excite the string like that, slightly different shape now. So the maximum of your initial excitation is right in a place where a mode is 0. This integral is probably going to be relatively small. If you really manage to set only that part of the string in motion, that mode will really not be excited much. So for the fundamental mode, like I was saying, the fundamental mode looks like this, right? So this integral is going to be relatively large if both f, the initial function, and the mode that is in the integral are large in the same places. So if you hit the string around its middle, you're going to excite the fundamental mode as efficiently as you possibly can. If you hit it near the endpoints, that's going to be the other way around. You still excite the fundamental mode a little bit. You always excite the fundamental mode because there's no place on the string where the fundamental mode is 0. That's why it's fundamental, right? But you won't excite it as much if you hit the string near a fixed endpoint. Okay, and that's why try it. If you or your neighbor or your roommate has a guitar, try that, and convince yourself. If you hit the string right at the middle, you're going to hear a relatively gray, deeper sound. If you hit it near the bridge, you're going to hear a more acute sound. I think it's good enough for one morning. Do you have any questions? So I leave you until Friday. Think about all these things, and as usual, try to come with your questions if you have any. Otherwise, we'll continue a bit more on this thing. There's one thing that I want you to think about to anticipate what I'm going to do on Friday. I might have disappointed you because we've solved the wave equations, but what we found, is it a wave? It's not really a wave according to our definition of waves, right? So it's kind of strange, I think, and I'll let you think about this a little bit, and you get the answer to this problem on Friday, hopefully. Okay? See you on Friday. See you on Friday.
Thank you, sir.
Ciao, bye-bye.
Thank you, sir.
Bye, 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 bye.